you think the biggest rush? I think Leo started to record. Great. I think he joined. Um,
Yeah.
yeah.
Yes, I'm here.
Great. Thank you. Hi, Leo. How are you?
Hi, how are you?
Good. Thanks.
Yeah, also
Sebastian, yesterday, I don't know why I was talking, and at some point I forgot to record the first part of your lecture. But we will have I mean, it's recorded in Zoom. I forgot to.
As a backup, I make sure it's recorded in Zoom automatically, and so now we can upload the video. So there's not an issue.
Yeah. Yes. My apologies.
That's what really happens. I mean, I recently chaired some talk, and then I prepared myself a sheet, start recording like that, big as as a page, and I mean, it didn't help. I mean, it just didn't help. So I oh God, I after 5 minutes or so, I realized I wasn't recording. But okay, that's life. There's worse things for sure. So
yes. Sorry, you have two lectures in a row. Hopefully, you can have recharging.
That's sporty, yeah. So after a day of preparing them, I'm not really looking forward, because I had to cut things down quite a bit.
Thank you.
No, I'm happy to. It's no problem. Actually, when I recorded my lectures for this term, I always did one big session instead of two separate ones. So we have 2 per week of 1.5 hours. I just recorded them in one go, because I mean, so it's demanding then, but on the other hand, you have it done for the week.
You have it done. Yes, that's true.
I'm somehow in good condition to talk for a long time. Yeah.
Thank you. Yes. I don't know. I mean, it has a lot of advantage, this recording the lectures. I agree. On the other hand, I mean,
I mean, what I start thinking, I mean, now you're saying this stuff, and then it's just said once and for all. Yeah. So next time you have to organize completely. Yeah? So but true. Yeah. I mean, these videos, these lecture videos, they are very well received. In our place, I mean, they like this. I mean, they can speed us up. They can make us go slower.
Yes.
They can rewatch things. So it's and then we have these Q&A sessions on top. So it's really, I think, the kind of understanding, if people take it seriously, invest that time, it can be even a bit deeper.
They can get deeper learning. Yes, I agree.
The questions that I get in these Q&As is 100 times better than, I mean, the usual questions. It's clear, yeah. Is there an I missing, a minus sign or so? Yes, and then the questions are rather really on the point, and it's really great. I mean,
yes.
So Sebastian, so much of your focus has been, sort of the technique, and that's wonderful, because you bring that those expertise to the students so they can develop these tools. But if I can encourage you to maybe comment, or even if briefly, on sort of the physical, content of the terms, let's say, that appear. For example, I don't know if I joined in late last time, if there's maybe some physical intuition about, for example, the 3 terms that appear in Lindblad and their corresponding terms in the Keldysh. It would be very helpful, just because we have, for example, lectures by David Hughes and other dynamical lectures on dynamics, which it'd be nice to make contact with.
No,
yours
he
is coming.
Leo, you missed it. He did discuss that.
That's kind of in the beginning, where I tried to really give the. I mean, okay, you can always.
No, that's fine. Then I might have just, I missed it because I came in a little late. So.
Yeah.
So it's good. Well, anyway, keep in mind that that's very. It's helpful, and it resonates very well when you're doing technical stuff, and resonated with complemented with the sort of physical commentary, whatever insight you have, it'd be nice to have it shared, physical insight, to have it shared with the students.
Yeah.
Okay, good. I'll try.
Yeah.
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 Okay.
Yes. Go
So
ahead.
maybe we should start.
Yes,
let's
great.
see.
So now,
Yeah, why don't we start? Yeah.
yeah, perfect. So welcome to our second day of the summer school this week. We're going to have 2 lectures in a row. One in the morning, separated both in the morning separated by a break. Sebastian Diehl will continue his lectures in this time on symmetry and topology in driven open quantum systems.
Yeah, thank you, Anna Maria. And yeah, let me come to the point. So I shortened a bit the lecture notes that are somehow online. And of course, if you like, you can have a look. So what I'm actually mostly missing or dropping out is the kind of classical or semi-classical side of things. And I want to focus now in this lecture number 2 on symmetries and topology out of equilibrium. So how I plan to do that, I mean, I would like to first, we have to kind of develop a little bit of language and feeling for 2 different things. One is the question in which sense is this Lindblad equation that we were studying yesterday, in which sense is this actually representing a non-equilibrium situation, and what the physical consequences of this non-equilibrium condition are. And on the other hand, I want to very briefly introduce to you this concept of dark states. And I think here, what stands here in the middle, that's how I feel that's really the focus of this lecture here. It will be revolving around the different properties that quantum states of matter have, and the dynamics that is happening on these on top of these quantum states in a sense that I will define. And one part of this story is actually that I would like to derive for you a response theory of dissipative out of equilibrium systems. So topological field theory, so we'll think about topology in these driven open quantum systems. And then I will use this as an occasion to walk you through how we can think about symmetries and symmetry breaking in this formulation. On the other hand, and that's the second part of this lecture here, I would like to talk about classifying, based on symmetries, classifying in and out of equilibrium dynamical systems. So it's again a story about states and dynamics, and how that relates to this recent discussion of non-Hermitian topology. What can we say about that when we start really from this microscopic Fock space kind of Lindblad dynamics here? Okay, so let's start with one of these background parts here. What is non-equilibrium about these systems? And the first thing that should be said here is that there's very different notions of what non-equilibrium can mean. And some people even say, thinking classifying physics into equilibrium and non-equilibrium is similar to classifying animals into elephants and non-elephants. Yeah, so it's not a very, very sharply defined feature, but let me still try. So on the one hand, we can think about time evolution as a source of non-thermodynamic equilibrium condition. That is the condition when time translation invariance is broken. And that actually indeed is the topic of the lecture of David Hughes, where I sneaked in briefly yesterday evening, and of these Floquet systems, which are evolving in time. And I think also Nigel Cooper and Tilman Esslinger will cover this. Now, what we are thinking about here is actually non-equilibrium conditions, even in the stationary state, when translational invariance in time is established. So we're looking at something that you could refer to as flux equilibrium states. And then the immediate question is, so in which sense is this representing non-equilibrium conditions, if we are in a stationary state? And the first insight that you should take home is that these non-equilibrium conditions are absolutely not encoded in the state of the system and in any kind of static observables that you could extract by looking at objects like that, trace of some operator with the stationary density matrix rho. That's not where non-equilibrium is encoded, simply because you can represent any positive semi-definite operator in terms of the exponential of some Hermitian operator. And that's not really telling you about anything, equilibrium or not. Instead, when you look at dynamical observables, for example, this simple example of a two-point correlation function in time, you will immediately see whether the system is in or out of equilibrium, because in that circumstance, when you look at these dynamical correlation functions, you will see what actually the generator of dynamics is that is acting on the system. Yeah? So the key point really to take home here is non-equilibrium conditions are encoded in the generator of dynamics. Yeah? And if and only if we can speak of thermal equilibrium, if this generator of dynamics is a time-independent Hamiltonian, which generates both the time evolution and shows up in the statistical weight of the stationary state. Otherwise, yeah, and that's this Lindblad condition where we have these Lindbladian operators around, so not everything is described exclusively in terms of age. We have to really expect non-equilibrium conditions, and then of course the question is, so does this matter or does it somehow average out? And this is of course a topic of figuring out in which sense. So even in let's go in a little more detail. Yeah. So thinking now about where do we encounter these non-equilibrium conditions? And maybe a first naive guess that I would also do is, okay, it must be somehow in the coupling to a bath. Yeah. So whenever that would be a naive expectation, when I have an open system that is coupled to a bath, I get some irreversible dynamics in my system. So that could be a source of non-purely Hamiltonian evolution. And one could expect, oh, that's already a non-equilibrium stationary state. The answer is, however, no, this circumstance is still compatible with thermal equilibrium. It is actually only when, in addition to the openness, the system is also driven. Yeah? So in other words, you should really very carefully watch how is the coupling to the bath going on, actually. Yeah? And this is signalized here, an equilibrium system. So this is really an important, as simple as it is, it's an important plot. Yeah? We can speak of a system in equilibrium if there is no driving frequency, yeah, which is in the system bath coupling, yeah, which couples these what will later be Lindblad operators, as we discussed it yesterday, coupled linearly to the bath. Here are the bath modes, and that's the system Hamiltonian. We can speak of equilibrium conditions when this drive frequency here is 0, or in other words, when we obey this scale sequence here. Yeah? So at least the drive should be the absolutely slowest scale in the problem, or let's set it to 0. So one can, of course, adiabatic vary this still, and we are in that equilibrium regime. The system has time to equilibrate, and the other scales, they are somehow on the same order of magnitude. Yeah? So this omega naught, the scale associated to the Hamiltonian of the system, and these epsilon mu's, the energies that are in the bath. So if they are all on the same order, then we are in equilibrium. And that's a very, very different situation from this non-equilibrium circumstance, where we somehow have the opposite sequence of scale. The system scale is much, much smaller than here in this example as the driving frequency, yeah, which I need to essentially bridge the energy gap to reach the order of magnitude of energies that the bath is having. Yeah, and then I can emit into this bath at a comparable frequency with this epsilon mu. So a very important point that is very easily overlooked, and it will really play a crucial role in the course of this lecture here, is that we are not only, this problem is not specified exclusively by specifying the system bath Hamiltonian, but when we think of a bath, we also specify the bath distribution function. Yeah. So, and this bath distribution function is fixed once and for all. And in particular, there is a frequency dependence of that. And that singles out a frame of reference, yeah, with which respect I measure all these energy scales in the problem. And therefore, it is not possible, yeah, to simply choose a rotating frame to get rid of this new scale. Yeah, so if I try, I can make this Hamiltonian here time independent by going into rotating frame. But then, because I fix the bath distribution function, this scale will shift around the zero of energy in the bath distribution function. So I don't get rid of that. And therefore, invariably, when I drive the system, I really can manifestly distinguish that from a undriven system. Yeah? And it's exactly this driven open nature that makes it incompatible with thermal equilibrium. So that is the physics discussion. Now we can think about how can we formally, without knowing much about the problem, detect. Now that's a really more mathematical question. How can we detect the presence of equilibrium conditions in a so to say model that I'm given? Yeah? And to this end, to explain how this works, let's go back again to this setting where we have a master equation, which consists of this coherent evolution by a Hamiltonian and this dissipative evolution, which consists of all these Lindblad operators. And as we said yesterday, this here morphs in the Keldysh language into a Hamiltonian contribution to the action, which I summarize here, and a dissipative contribution, which is essentially the functional integral representation of the dissipative dynamics. And as we just discussed, yeah, equilibrium dynamics, we expect that to be generated microscopically entirely by an undriven time-independent Hamiltonian. So in that circumstance, we would just set SD, this dissipative contribution, to 0. Yeah? Let's do this by hand and then see, can I find something in this action that already anticipates that I have equilibrium condition. And indeed, this is true. There's a funny symmetry. So that's our first encounter with symmetry in this Keldysh formulation. And here is the transformation. I don't expect that it's immediately transparent, but I can describe it and later will actually interpret this in much more depth. First of all, you see that I'm sending under this transformation t to minus t. So it seems to have to do with time reversal. And in fact, it has to do with time reversal. And there is also a funny shift into the complex time plane, yeah, by a parameter I beta, which has dimension of time. And it can be interpreted actually as 1 over temperature. But it's a free parameter in this transformation. And the statement is any action of this type SH, which represents a time-independent Hamiltonian, any action of that type enjoys this funny symmetry here, which is a discrete symmetry that squares to 1. Okay, now
so your temperature is set by the bath?
Yeah.
So your temperature is set by the bath?
That at this point, this beta parameter is a free parameter in this. It's just a kind of, if you like, it's a 1 parameter symmetry transformation. I have 1 parameter for free, and I can choose this. If I only have a Hamiltonian, I can choose it for free. However, if you think about an action that picks up something that we discussed briefly yesterday, if you only have a Hamiltonian action, this functional integral here is not well defined. Yeah, you have to regularize it. You have to give it an I epsilon prescription. And it turns out the only way to do an I epsilon prescription, yeah, which is compatible with this symmetry, involves indeed a distribution function, which for bosons is this, and for fermions So it would come something like that with an epsilon tanh for bosons or for fermions respectively. Yeah. And when you add such a term, yeah, then this parameter that occurs in the transformation and occurs in the function, they are the same. Yeah. So the statement is, if you like, more physically, any temperature is fine with conditions of thermodynamic equilibrium. Yeah? But if you choose one, then you have no more freedom in choosing this symmetry.
So in general, in Hamiltonian systems, when you thermalize, this beta is set by the initial energy. So you don't have a condition like that yet.
Yeah, that you can say. Yeah. So if you think about a thermalizing dynamics and you initialize it with some mean energy, that will somehow transform into this beta parameter, into the mean temperature. Yeah. Mean energy is this temperature. Yeah.
But isn't there beta sitting in the S of D? Like S of D comes from integrating out the bath, right?
If we have a master equation, yes, it would come from integrating out this driven baths that we were looking at. If we have say what is called the Caldera-Leggett model, yeah, then we couple to an equilibrium bath. Yeah, so if we are somehow in that circumstance, we can also couple to a bath. And if we then integrate it out, then we will discover, okay, there is a dissipative contribution which comes already with the distribution functions, yeah,
I see,
that I have implemented by choosing a bath. And also in that circumstance, of course, this parameter beta is then fixed by the bath. So there's let's think about this in two cases. Yeah? One is the case of self-thermalization. Yeah. So the system is interacting and it finds its thermal state, and the mean initial energy transmutes into the scale of temperature. Yeah. The other option that we have is, okay, we could also directly couple it to a bath under conditions of global detailed balance, so no drive in the problem. And then this beta would be fixed by the bath by integrating out this equilibrium bath.
Okay.
But if we have now this additional scale of driving, yeah, as I said, then you cannot gauge this scale out of the problem. And then the point will be that this symmetry is then absent. Yeah? So you will kill this symmetry by non-equilibrium condition. Okay?
Can I ask about this driving?
Yeah, please.
I guess I was a little confused. Is this drive only in the coupling of baths to the system, or can it be like an external drive?
This is typically it is a external drive. Yeah? So I mean, if you have this circumstance here, yeah, we can make an example, the example that we did yesterday. Yeah? So a two-level system. And then this here is new. So we have some spacing, yeah, the spacing of this ground and excited state. Yeah. And then we go for this level up to some detuning new. Yeah. And that's then kind of, and it comes with a strength G mu, yeah, which in that context you would say is the laser intensity omega. Yeah. So that's typically indeed a classical field. So a laser field with which you drive this quantum system. It's absolutely correct. More questions? The first parts are always the most important ones to set this. So I would really love if that is more clear.
Just making sure I understand. When you say that the temperature, the shift is a symmetry of the Keldysh, are we saying that the trace remains, like Z remains 1 upon the integration? Or are we saying that the action itself has the symmetry?
Yeah. And so if you want that really technically, the statement is that under this T beta of the acting on the fields, yeah, and then I still have here this I to minus I, so I have to take star. That's the same as the initial one, and also I have that the functional measure here is also invariant. That's the statements that we have. So under this, that's really.
All right, thank you.
So when you say that
nice exercise.
Mhm.
But I want to give you the interpretation of it. I mean, I don't have an interpretation of this mathematical transformation, but I can give you immediately what it has as consequences. So should I maybe specify the consequences and I take the question then? Because that may already clarify a bit. Yeah. So really the physical meaning of this transformation is when I look at what are actually the consequences of this symmetry. Yeah? So what I can do as a conceptually, I can apply this T beta transformation to the partition function, and I know that it's invariant. Yeah. And then I can do the same thing for operators. Yeah. So, and I also have that they should be invariant under this symmetry transformation. Yeah. And if I use this invariance of correlation functions, then that's what you call ward identities associated to these symmetries. And interestingly, these ward identities are really what is called fluctuation dissipation relations of thermal equilibrium. For example, we yesterday discussed this correlation Green's function, the Keldysh Green's function, and we discussed the response Green's functions. Yeah, G retarded, and advanced Green's function. And if you look at the consequences of this relation here, of this symmetry relation, then you find that these functions here are actually absolutely not independent. Yeah? If I give you the response function, or even the imaginary part, so the G retarded minus G advanced is a spectral density. If I give you this function, I have immediately this one here determined. Yeah? And that is what one calls fluctuation dissipation relation, and that here where the distribution function here displayed for bosons shows up. Yeah? So what I would like to, I honestly cannot give you the deepest meaning of the symmetry transformation, but I can give you the immediate consequences of it. That are these fluctuation dissipation relations. I have displayed that in for the single particle Green's function that we discussed yesterday. But in fact, the symmetry is a compact way of formulating these fluctuation dissipation relations to arbitrary order. So arbitrary correlation and response functions will be related by the power of the symmetry in a non-trivial way, as we see it here in a concrete example. And this is nothing but what one calls the definition of detailed balance, yeah? That all correlation and all response functions are related to each other by essentially only the distribution function of bosons and fermions. So that's this symmetry. And now the statement is the Lindbladian. When I write a Lindbladian action, so I have this SD non-zero, then this is immediately gone, this symmetry. Okay? And the intuition is really that we are then dealing with a driven system, and we should not, by this physical discussion, expect any equilibrium. Now, sorry for letting you wait a bit. Please ask. So I still can't see the names, sorry. Just
yeah. So I have a question about the master equation and the starting point. So here we are looking at a reduced density matrix for the system, right? So in that case, we are tracing out the Bath degrees of freedom. Now, similarly, if we come back to the Keldysh formalism, so won't we lose information about the Bath if we just use the reduced density matrix? And
how we use that, you mean?
Yeah, I mean, if we are just looking at the reduced density matrix, then
it's I mean, in very, very brief terms, you have rho, which is a rho system times rho Bath, in some approximation. So an approximation. You take a trace over the Bath degrees of freedom here on both sides, and you do a second order perturbation theory, where essentially you expand something like e to the Bath operator times Lindblad operator here to something like 1 plus I BS L to second order plus B L squared, yeah, and all combinations of it. And then you essentially trace at second order, for example, you get something like rho B, B dagger, B trace B over that. And that is, of course, nothing but a correlation function of the bath. Okay, that's how that enters. We said we do a second order perturbation theory, yeah, in this time-dependent second order perturbation theory. So that's the rough structure how that works. Huh? And again, I specify this explicitly in the appendix if you want to have a look in the path integral language, but it's the same manipulation. Please, other question?
So maybe you've already said this, but when we're saying that it's that the equilibrium dynamics are microscopically generated by an undriven time-independent Hamiltonian, but we still can have coupling to a bath as long as the bath is not driven. Is that what you're saying? Like, I mean, we know that we can have equilibrium if we couple to a bath. So are we just?
So it's essentially two opposite kinds of limits. Yeah? To me, I mean, it's most resonating when you have this picture. Equilibrium is really, so I can always write the system bath coupling, yeah, as in this form, yeah, but I can occasionally choose this nu equals 0. Yeah? That's what we call an undriven system. And then you can see, okay, so that we have some overlap of some possibility to emit into the bath. Yeah? I need the energies of the bath and of the system to be roughly the same. Yeah? So all scales are roughly of the same order. Now, in a driven system, you, by definition, or that's really the definition, you always have one very, very fast scale, yeah, or maybe a bunch of fast scales. At least you have a big energy separation between the system Hamiltonian and these bath modes here. And you cannot gauge this out, yeah, this drive scale. And why you cannot gauge this out? This is because we are fixing the bath distribution function once and for all. We want this as a reservoir. That's the definition of a bath, a part of the system that is much, much bigger than the system itself and that never changes if the system undergoes time changes.
Right. So I guess on the next slide, when you say that D of rho is 0, like the dissipative driven part is 0, that assumes like that if we did have some dissipation that we've like gauged it out effectively, or like by saying because the one body.
I mean, you mean when I set some of this dissipative part to 0?
Yes, right.
That was again this discussion. I mean, you can go two ways. Yeah, you can have Hamiltonian alone with interactions. Then it can self-thermalize. But microscopically, this problem is really specified with the Hamiltonian alone. Yeah? So that's kind of the system acts as its own bath. That's the phenomenon of thermalization. You could look at that. Yeah? So that's one way of looking at thermalization, is the system acts as its own bath. The other way is already to start with H plus H system plus H system bath. Yeah? And then you integrate out the bath modes. And then you get immediately a dissipative action. Yeah, you get some dissipation immediately from eliminating this bath. And then you have to be careful, is this in equilibrium or out of? Yeah, and this is nu equals 0, and that is nu much bigger than other scales. Okay, that's the rough structure. Yeah. So, and these parts here, they really count together, yeah? While this here is a separate story. That's the point I want to make. Okay, is it a bit clearer?
So we're not actually requiring that S of sub D is 0. We're just requiring that if it's non-zero, it has.
I mean, for the sake of explanation. Yeah? So assume, yeah, for that exercise here, yeah, that if it's 0, then I under guarantee I have this symmetry here. But whenever I stay in this class of systems here, I also have this symmetry. Yeah. So this is the class of equilibrium systems, and this here is the class of non-equilibrium. Yeah. And these are really the driven ones. Okay. So, I mean, maybe another way of saying it is like that. Yeah. I have unitary, purely unitary evolution. That picture will come later on. Then I have irreversible equilibrium evolution, and even around that is irreversible non-equilibrium. Yeah? So you can look at this irreversible equilibrium as a very special, as the special case of thermal equilibrium in the most general non-equilibrium evolution, yeah? Irreversible non-equilibrium evolution. A special class is irreversible equilibrium evolution, and within this there is a subclass of purely unitary dynamics. And now if this dynamics, this purely unitary dynamics is interacting and self-thermalizing, counterexamples are of course many-body localization. So then a microscopically unitary system will somehow easily flow, if you like, under coarse graining, under randomization group transformations at long wavelengths. These systems always look dissipative and in that sense become irreversible. The system acts as its own path. Okay? This is maybe a good picture that can clarify this a bit. Okay, further questions.
This transformation, this minus I, like minus t plus I beta 2, this sort of reminds of that the imaginary time formalism, or that mapping the t-dimensional quantum system to t plus 1. Is it related to that?
It is, I mean, it is related in the sense that, I mean, whenever you have this imaginary time formalism, yeah, what you do is essentially to use the analogy of this here, which, as we said yesterday, is a string is evolving a time string in a one-way direction, and you can do a path integral to get a real-time Feynman path integral. So this imaginary time formalism is just saying, okay, IT, I can write it as beta, and then likewise, I have some more periodic boundary conditions, and I can do my imaginary time path integral. But I would, if you do it like that, you confine yourself from scratch to equilibrium conditions. Yeah? While in this more general Keldysh formulation, thermal equilibrium shows up as a special case. Yeah? And this special case is distinguished by the presence of this special symmetry. Yeah? And then you can ask, if I give you some action, yeah? If I give you a Lindbladian and you translate it into the Keldysh, I can ask you, does it have the symmetry or not? Yeah? And then you can go and check. Yeah? And then you will see, no, these Lindbladian actions, they don't have this symmetry. And again, the physical reason is that we are in, then these Lindbladians, they are in the most general type of evolution that can happen. Yeah? Symmetry is always to be seen as something that is, symmetry is some extra that you add. Yeah?
I was thinking maybe the fluctuation dissipation comes from this mapping, and maybe that's the reason why.
Fluctuation dissipation relation, yeah, is indeed it is somehow implied, yeah, by this symmetry. And you are completely right, yeah, that if I look at a thermodynamic equilibrium system, it always will enjoy this fluctuation dissipation relation. However, what I'm saying is, if you work in the imaginary time formalism, this is hammered in line 1. Yeah? And we don't want to hammer this in line 1. We want to be more flexible. Okay? Good. Great questions. Okay. Unfortunately, I'm on page 3 of.
That's okay. That's okay. That is good.
Doesn't matter. Okay. So some other piece of background that I would like to provide this is the concept of dark states. Yeah? So this is a concept that will be the non-equilibrium analog of ground states, if you like. Yeah? So that's how we will use them and then figure out distinctions between states and dynamics. So we first need a good notion of what is a ground state. So these are now these dark states, and what these are is explained here. So let's for a moment forget completely about this coherent evolution and just focus on this driven dissipative one. Now, the definition of a dark state is by this elementary condition here. It is a state D, yeah, that is annihilated by the entire set of these Lindblad operators Li. Yeah? So what you can clearly see, if we really stick to forgetting about the Hamiltonian for a second now, for explaining that, then you see that whenever the system, the density matrix is exactly in this dark state, is a pure state spanned by this dark state, then the time evolution stops. So that's a kind of dynamical fixed point of this Lindblad evolution, where if you're in there, you are stopping the dynamics. And it becomes in particular interesting when there's really a unique dark state solution. Yeah? What we have in that, so that means that the space spanned by all dark states is really one-dimensional. There's only one dark state, and it also means that there's no other solutions in this master equation, which could, for example, come from this term canceling this term. Yeah? We really insist on Li on D equals 0. Yeah? So that's, if this is unique, then you can immediately conclude, yeah, that you have this situation of a state which you can enter but not leave. Yeah? So wherever I start in my Hilbert space, then I will be able to find a sequence of jumps, yeah, which are, let's say, coming from these jump operators here, which will connect me down to this dark state. Yeah? So, and the uniqueness is some of the requirement that there's no subspaces in Hilbert space in which I can get trapped. Yeah? That may be also an interesting situation, but let's discard this.
But Sebastian, cannot you have symmetries that allow you to have more than one dark state?
That is absolutely possible. For example, in this topological dissipation-induced dynamics, we have subspaces, yeah, that are more dimensional. For example, they are spanned by two states of different parity. So that's definitely possible. But here, I mean, looking at the bulk of systems, and I need the analog of this ground state condition, of a unique ground state, if you like. Okay. Yeah, of course, if you, for example, open up the system, put boundaries or so.
Okay.
Okay, so we get a directed motion in Hilbert space. And interestingly, yeah, if you really buy this, yeah, then you can say that any initial density matrix that I start the system with, it might be a maybe complicated mixed state, will end up in a pure state. Yeah? So that's a pure state, a projector. Yeah? And so in this way, you can use dissipation to actually remove entropy from a system. So that's really like a bit like a fridge works. And so the picture is that you can remove entropy. Yeah? At least what you will have is an entropy outflow of the system, which will transfer the entropy in the bath, so into the bath, which is unchanged because it's infinitely much bigger, and then you end up in a pure state of the system. So that's quite remarkable in the sense of physically thinking about that. Usually you would say dissipation is something like friction. You rub your hands and everyone knows this creates heat and so on. So you're actually increasing the entropy, but in this case, yeah, mathematically, in the presence of a unique dark state solution, you can actually extract by these arguments here entropy. Yeah, you have an entropy outflow, and in fact, there's nothing fundamentally wrong with that, because it's not saying that the entropy of the total system and bath is reduced. It's just saying that I'm pushing the entropy from the system into the bath. Yeah? That's only possible in driven systems. So that's kind of the strong side of driven systems, if you like.
Can you have a dark mixed state, and how would you interpret that?
That's not then somehow what would be in the name. So that's not in the definition. Yeah? So I mean, then we don't call it a dark state anymore. Yeah? We can have So if, for example, that's what I'm saying, if I have di's, yeah, and I or dl, and L goes from 1 to n, yeah, something, yeah, and each of these dl's obeys this condition here, yeah, then I will end up in a subspace, yeah, which is n-dimensional, and in this subspace I don't purify, my Lindblad operators do not purify anymore. So then I will end up in a mixed state spanned by all of these guys here. That can happen. And that's why I want to really look at this pristine situation of a unique one. Yeah? So I want this n equals 1. That's it. Yeah? Just for convenience. But it's possible. Yeah. Okay.
Excuse me.
Yeah.
Why did you cross out the loops? Why can't you have like some kind of cycle in the Hilbert space?
Hey, you can have it, yeah. But I want to look at that situation. Yeah? So it's not in principle impossible. I just wanted to say under which circumstances do we have somehow the analog of a unique ground state. Yeah? And that actually, to be honest, it's not easy to diagnose or to prove, yeah, that these conditions that I'm happily formulating here are present. Yeah? It's in a big many-body system. It may be even more complicated than showing that the ground state of a Hamiltonian is unique. Yeah? That's also not so easy. Yeah? So I'm just formulating conditions, but I'm not telling you if they are realized. We can, from case to case, you can of course check that. Yeah? Try to check it.
I see, but so it's not immediately obvious, like a simple condition that would prevent you from having those.
I want to create kind of an analog of a unique ground state. Yeah? Mm-hmm. And you are completely right. Yeah?
Okay, thanks.
Yeah. Okay, let's look at an example. Yeah. So, and there's a trivial example. Yeah. So let's look at a decaying cavity that has a beautiful dark state. Yeah. So a decaying cavity, my Hamiltonian, I set this to 0. Let's keep it simple, not even some oscillatory motion going on in this cavity. And as Lindblad operators, just a single photon loss from the cavity. Yeah. So that dynamics has a trivial dark state indeed. Yeah. You can see when my system is in some number, in some occupation mode n, yeah, then this deletion operator will always transport me down to this 0 level. So the dark state, we have a beautiful but dark state, which is so where the evolution stops, yeah, simply because A acting on 0 is 0. So that's a dark state condition for the single Lindblad operator L. And that's of course what you refer to as a trivial vacuum. Yeah? So no particles in there. There is a little more interesting circumstance. Yeah? When we look at a many-body problem, and that's what we'll do now, we look at a topological insulator dark state. Yeah? I will specify Lindblad operators that actually annihilate a state of matter which coincides with the ground state of some Hamiltonian, which is a topological insulator Hamiltonian. And then we speak, of course, that's a state with many particles in there. Yeah? So that's an insulating state which is filled with particles. That's what one then calls a non-trivial vacuum state, yeah? As opposed to this trivial particle empty vacuum state. Okay, so that brings me to this part of the discussion. And let me now come to this point. Now we have states, discussed states. Let me now come back, connect this back to the discussion of dynamics that we started from in the first part of this lecture. So we look at here a quite general quantum evolution generated by this Lindbladian here. And I can make this distinction between dynamics and states based on, again, this simple harmonic oscillator example. Yeah? So this quantum cavity problem again. Yeah? So now we could look at a Hamiltonian general case, yeah, with some scale omega naught, some oscillation scale, and a photon loss Lindblad operator like that, as previously. Now we have again the choice of studying two extreme limiting cases. Yeah? One limiting case would be, okay, kappa is 0, so I forget about the cavity now. So it's a perfect cavity, no loss at all. Then the evolution is just this von Neumann equation. So that's really the Schrödinger equation for mixed state, as David called it. Or we could look at the other extreme limiting case where my frequency is 0. That's the one we looked at previously. And I just, so in this dark state discussion, and I just have this evolution, yeah? Only lossy evolution. Now, what can we say about stationary states of that problem? Well, this here is an evolution that is purely governed by a Hamiltonian, yeah? So an undriven problem. So that will have stationary solutions wherein the exponent of the density matrix appears the only generator of dynamics H, and beta is, as we said, given essentially by the initial state of the initial mean energy of that system. In particular, if I choose the initial condition beta such that beta goes to infinity, so that's of course the same as temperature going to 0, then I reach as the stationary state of this dynamics, the ground state of this Hamiltonian. Yeah? So that's certainly the ground state, A applied to 0 equals 0. That's a positive operator. So that's a ground state. Okay. Conversely, I can stabilize here, but I can calculate the non-equilibrium conceptually, the non-equilibrium stationary state, which is a dark state here, as we said previously. And it's, of course, the same empty vacuum state. Yeah? So it's all trivial physically. What I want to notice is that they really coincide. If conversely, I look now at the dynamical response of this problem, I get a completely different story. Yeah? So the response, as we discussed it yesterday, yeah, I could generate a response by coupling to some, maybe I should put this classical source. Yeah, I start to couple this to a classical field here, and then I study the response as we did it yesterday. And in the case that kappa equals 0, I would get a reversible equilibrium response, yeah, that follows the signal that I start, initialize at t equals 0, and after that I would get this oscillatory response here. Yeah? And that's of course completely different from the response that I compute for the same setting. Yeah? I also start to put an external field, and I would get an entirely decaying response. Yeah? So that's essentially the two extreme limits of the example that we studied yesterday, yeah, by choice of these two scales. So the upshot of this discussion is not that it's interesting physics, but it's conceptually interesting to see that we can have the very same stationary state or dark state, but completely different dynamics acting on it. Yeah. And now we come
just to kind of put a finger on it, you're saying that these different types of dynamics lead to the same state of the system. Is that correct?
Yes, the very different kinds of dynamics will reach the same, can reach the same.
So I'm imagining two different experimental apparatus, one of them with kappa equals 0, one with omega equals 0. Yeah. But if I just look at the state after infinite amount of time, I'm looking at the exact same system. I couldn't tell you which one's which.
Exactly. So right. So you can right. Yeah. So I mean, to be honest, I mean, to achieve this situation, you should now, because it's a non-interacting Hamiltonian, you should have an infinitesimally small coupling to a bath, yeah, so that indeed it reaches the state. Yeah. And the bath should have a temperature beta. So according to this discussion that we did previously. Still, yeah, if this coupling is infinitesimally weak, then you will get this purely reversible response, yeah, up to really infinitesimal corrections. That's the point. Yeah. So really, I want to stress that states can be the same, but dynamics on top of it can be very different. Yeah? And I now want to put this into the
sorry, I have another question.
Mm-hmm.
So for the response, were you specifically saying, like, say, the retarded Green function, or it's just a response where, I guess you put a J in the system? Or...
Yeah.
Okay.
Can you say it again? I mean, that's what we did yesterday. So
oh, okay. So it's a. Oh, okay. Cool. Yeah. Thank you.
that was really the kind of, you can look at this formula from yesterday and take these limiting cases, you will find these two. Yeah?
Can I also ask just a little bit, remind me about the, this damped harmonic oscillator. What's, so you have bosons, which are the harmonic oscillator, the mode in the cavity, but what is, are there photons, or do you have to describe photons outside the cavity, or what's doing the damping? Is it just the fact that, well, if I take a concrete example of the cavity.
It's the coupling to the outside photons, yeah, right. Yeah. To the radiation field outside of the cavity. So you have some A is coupled to a whole set of mu's, yeah.
I see.
And that's really external world. Yeah.
Okay, so that's your, I mean, in a language of Caldera-Leggett, that's the kind of term I would put in. I would integrate out B's.
That's exactly right. Yeah. However, now we have this guy.
I see.
But
we can't gauge it out. Yeah. As I said, I mean, we cannot gauge it out because the state of the bath is fixed. And this puts a frame of reference, if you like. And so
no, I didn't mean gauge it out. I meant integrate it out.
But that's what it has been done when you get the master equation. That's
exactly.
how you get. I mean, that's what leads to the master equation. You integrate the bath and give you the
Sure. That's okay. I just want to make sure I understand what the underlying physics of the Okay, so it's this A-B dagger. Okay. Thank you.
So these processes always come up. Okay.
Just to confirm one thing, are gamma and kappa the same here? I mean, like the exponent of the decay rate.
Oh, did I say
given by kappa?
So this is kappa and gamma. Yeah. But, sorry. Yeah, absolutely. Yeah. Okay. Good. Thanks. So other questions? So then I can enter topology, yeah. And so I mean, one thing you probably, or I'm just telling you that that's what it is. Yeah? So usually it's a known thing that topology is something that is really encoded in the wave function, in the ground state wave function, yeah, and kind of knots in the ground state wave function that are measured then by winding numbers, by Chern numbers or something, but it's really a property of the state of the system. However, when you want to observe consequences of topology, yeah, then you typically look at dynamical responses. Yeah? For example, you look at how a system responds to external gauge fields. Yeah? And in this way, you get going, for example, on the edges of a system, yeah, by applying external fields, you get going something like that is called the chiral edge modes, yeah? For example, on top of a quantum Hall state. Yeah? So while the basic phenomenon is in the state, observables are often dynamical. Yeah? So the question then is, can we have so a topological response, yeah? So on top of an irreversible out of equilibrium dynamics, yeah? And even more operationally, you can ask, so it's kind of not what you would believe immediately. Yeah. So when you have a purely dissipative bulk system, yeah. So how should it be that on large observable length scales there is some reversible action sitting, yeah, some reversible dynamics going on, yeah. So which is described by this propagating and not damped chiral edge modes. Yeah. So, and that is now somehow the question that we would like to answer. Yeah. So is there, I mean, technically speaking, is there a topological response in an irreversible equilibrium, out of equilibrium dynamics? And then more operationally, are there, for example, consequences that are familiar from equilibrium ground states, like these reversible edge modes, yeah, which propagate in an almost undamped way. Okay, and so here comes now the scenario in which we want to work. So I want to compare a Hamiltonian scenario to this Lindblad scenario, where the Hamiltonian scenario is characterized by a unique ground state, which could be this Chern insulator state, yeah, which is nothing but this. We have two bands in a system and a big band gap, delta here. The upper band is completely empty, yeah, and the lower band is completely filled. That's a situation, yeah, in which this Chern insulating state can live. Okay? And I'll come to the more concrete example next. Okay, and then I want to confront with a Lindblad scenario where we have a unique dark state, which is characterized by this condition, so formally pretty similar, which is a dissipative Chern insulator. So we'll engineer a dissipative dynamics that pushes all the particles from some upper band into some lower band, and in this way stabilizes really the same state as we can have as a dark state of as a ground state of a Hamiltonian. Yeah? However, as I was already anticipating, now in the one case, the dynamics that the system is undergoing is really a reversible unitary evolution, which respects detailed balance. And I want to confront this with the irreversible dissipative evolution governed by a purely Lindbladian equation. And so this is really the analogy of the purely oscillating cavity mode versus the purely decaying cavity mode. There we have seen the response is extremely different. Now we're asking, can topology do something for us and maybe stabilize the response that the ground state system also exhibits? So that's the basic question. And here is the model in which we want to answer this question. So we start now on this side of things, where we have this Hamiltonian. And so it's enough to take a quadratic Hamiltonian here, which is written in momentum space. So this is the vector of Pauli matrices sigma x, y, z, which defines essentially the two-level systems for each of these momentum modes Q. So that's a typical setting for a topological insulator. And it's a useful thing to diagonalize this Hamiltonian. So we do a basis transformation where these operators here show up, and in the middle I have a diagonal matrix, just sigma z, showing up, and I can reorganize this in this way here. So here are the original creation and annihilation operators, and here are the eigen operators. So in which spaces the Hamiltonian is diagonal. And as a concrete example for this vector D, but it's not really extremely important, we can, for example, take this form here. That's a Chern insulator, so-called class A. Okay, so then we can find the ground state when we have it in the diagonal form. So I can write this here as L1 for each Q, dagger L1, minus, because of the sigma z, L2, dagger L2. And I want a state that minimizes the energy of that. That's a positive operator. So a ground state is certainly a state which is annihilated by this operators L1. Now for these guys here, there's a negative sign in front. So if I look at L2, ground state equals 0, then I get actually a state of maximal energy. So let me therefore rearrange these things, minus, and then using fermionic computation relations. In this way, now these two signs find a plus. So I see the lowest energy state is actually by this condition that L2 dagger annihilates the ground state. So these two conditions here define the ground state condition for this Hamiltonian operator. Okay. And with this ground state condition, I can now devise a dissipative dynamics, which has the same state as a dark state. Namely, I simply take these guys here as Lindblad operators, in this way here, L1 and L2 dagger. And what they will do, they act very similarly to this cavity decay with one catch. L1 on D equals 0 means that the band 1, the upper band, is completely emptied, yeah, while L2 dagger on this dark state being 0 means that this is completely filled by Pauli principle. Huh? We're speaking of Fermat here. So that condition, that defines, these two conditions define a dark state for this problem, where the intuition is really so that I'm emptying everyone that is in the upper band and I'm filling everyone up that is in the lower band. Okay?
So you need a unit filling conditions for the lower band to have.
Exactly. Yeah? So that's really this exactly. I need half filling of the entire system.
Mm-hmm.
Mm-hmm. Good. Now there's a fine print in this, namely in this model. If I do it like that, yeah, I have Lindblad operators which are really coupling these fermions out of the system that I'm describing with this Lindblad equation. So this is certainly not conserving the system's particle number. Yeah? I can also do this trick here. I can choose these guys here as Lindblad operators. Yeah? These you should read them as an if-then condition. If L1 on this dark state is 0, then the time evolution stops. If it's not 0, yeah, so but it projects me into some other state, yeah, for example, from here I'm going to there, then this evolution will just continue. Yeah? But what you can read off from this kind of structure is, one thing is for sure, again, this dynamics will come to an end, will stop when I fulfill these conditions here. Yeah? What that buys me, yeah, this if-then idea, buys me the following thing. This operator here is only reshuffling particles into another state, but it's not shooting them out from the system. Yeah? So it's doing moves like that. It's moving particles from here to there, and maybe from here again to there, and so on. Yeah? So it's moving particles around, but I'm not coupling them to the outer world. Yeah? So the problem with this is, of course, that's a problem, yeah, which is not non-interacting. Yeah? So that is, if you count the Lindblad form is of this type here, it involves 2 times 2 operators, so that's an interacting problem. Okay, but what's the physical consequence or physical difference between these? So in this case, yeah, if I look, as I said, yeah, if we look at a situation and I look at the evolution of the local density operator, yeah, I can compute that, yeah, and then I find, oh, this is actually not an equation which only has a gradient of some current, so maybe I start better on that side here. If I'm in this number conserving situation and I compute the time evolution of the local density, then here on the other hand, I definitely get a gradient of some current operator. Yeah. And the reason is, yeah, that particle number is conserved. So if I sum over all x and of x, and I do that on both sides, yeah, then this here is 0, and therefore dt and x is 0, and this is total particle number. So total particle number is conserved, yeah, in this circumstance. On that side here, I will find a correction which is not of this gradient form, so it's not a conserved particle number. So that's 2 different situations. Yeah? Again, I have the same dark state, but very different dynamics running on it. Yeah? Okay, so what we'll do in the following is to look at this model M2, actually in more detail. So here is then the program, and I'm really starting a bit to wonder how far I will get, but yeah, maybe I just start. So we want to compute now the topology of this that is associated to the response of these states here. And the plan is, okay, let's first map it into a Keldysh functional integral. That's essentially what we did yesterday. Then I would like to really discuss a bit a technical point with you that is kind of thinking about symmetries in this Keldysh formalism. And then we can study, based on that, we can study the response of these states by coupling it to, by a minimal coupling to the electromagnetic field. Okay? And from that minimal coupling to the electromagnetic field, we can compute then the response of these states. So that's a bit the plan. Okay, so let's start a bit with discussing symmetries in this Keldysh formalism. So as a recap, yesterday we discussed this closed time path formulation here, where we have this Keldysh contours, plus contour minus contour corresponding to the density matrix evolution. This Lindblad Keldysh action obtained by taking every operator that acts on the left to the density matrix and put it on the minus contour, and everyone that acts from the right, put it on the plus contour. So that is this Keldysh Lindblad action. Yeah? So in particular, we are equipped with these two branches here, plus and minus. And we also discussed that we want to introduce these classical fields. So that's the occupation fields, as we discussed. And that is somehow here, well, a quantum field that has nothing to do with occupation, but rather is a tool to generate response functions. Yeah? Okay, now with this interesting plus and minus contour structure, it's immediately clear that also when you do symmetry transformations, like these phase rotation transformations, you have the possibility, in principle, of doing this independently on both these contours, right? So you can do transformations on the plus and on the minus contour according to this formula here. And so therefore, we have also two variants of this U1 symmetry, a U1 on the plus of this phase rotation transformation, a U1 on the plus and on the minus contour. And as we did it for the fields, also for the symmetry generators here, I can choose a new basis and go to this center of mass symmetry transformation and to this difference relative symmetry transformation. Okay, now what does this tell me physically? And that's actually a topic that connects to these works here, for example, where the authors discuss the differences between strong and weak symmetries. Yeah? And that is something that I would like to discuss now for this example of this continuous global U1 symmetry. So we speak of strong symmetries if we can really do independent transformations on both contours. So I can do a transformation e to the I chi plus minus, psi plus minus, independently on both contours. Yeah, so I have a U1 plus cross U minus. And that is, of course, equivalent, yeah, by just counting the number of generators of this transformation, of having this combined structure of classical times quantum transformations. So, and I want to show you that this kind of constellation here gives rise to conservation laws. Yeah? So, and there's gapless modes associated to these transformations here, which are representing hydrodynamic modes. So that's continuity equations that you get when you have these strong symmetries. Conversely, if we have weak symmetries, so we only have one single generator, namely we have only an invariance under this, the in-phase transformation, then we don't have conservation laws in the problem, but there can be still interesting consequences of that, in the sense of these are the symmetries that can be spontaneously broken. Yeah? And then there can also be Goldstone mode, gapless modes associated with these broken symmetries here, spontaneously broken symmetries, which are Goldstone modes. Yeah? So we will study here consequences of these two very different symmetry patterns that we can have in these Lindblad equations.
Sebastian, can you say in this formulation,
yeah,
I mean, if you go back for a second, the hydrodynamic modes, you need both you need both U1s, or are there some hydrodynamic modes also in the weak symmetry case?
No, in the weak symmetry, there is no conservation laws and no hydrodynamic modes. And I want to explain it now.
Okay.
Yeah. Okay. Good. So let's first, I mean, I have it here in the reverse order. I have first strong and then weak. Let's now look first at this weak symmetry part. Yeah. And then I recall this generic Lindblad model that we had yesterday. Yeah, so which consisted of a Hamiltonian, which is kinetic energy and two particle interactions. And then we have the single particle pump with a rate gamma pump. We have the single particle loss, and we have two particle losses here. Now, what's the symmetries in this problem? Well, we for sure have a U1 classical invariance, where we transform both these Keldysh contours in phase, in formulas in terms of the master equation. I can send the field operators on the left and on the right. I can subject them to one and the same transformation chi, and then you see here a dagger, here no dagger, they just cancel out. What I cannot do is to transform this guy here with the e to the I chi plus and this here with the e to the I chi minus. Then, so there's a relative sign because there's a dagger here. These would not cancel unless chi plus equals chi minus. So there's only one single U1 symmetry in this problem. And that's an instance of a weak symmetry now. U1 quantum is not there. And now I want to, in this simple scenario, I want to now look at physics. It's spontaneous. I want to make the point that this weak symmetry is the one that is associated to this phenomenon that you may know, spontaneous symmetry breaking. While this quantum symmetry is associated to hydrodynamics. Next thing. Okay, so here, let's look at this weak symmetry here. And how would we see, I mean, if you look at this equation, I would say it's very complicated, or I wouldn't have the right language to speak about spontaneous symmetry breaking. It's all operators here, and that's not really a good framework to speak about spontaneous symmetry breaking. Instead, we go now to the Keldysh action formulation. So we map this into this Keldysh field theory, what we already did yesterday. And here I just reproduce this formula. So here you see the single particle sector, this PR, and here this loss and pumping add up, as we said yesterday. And here's a bunch of interaction terms that come just from processing all these terms to this Keldysh construction. Okay, let's now assume that the system, I want to make now a point that is associated to this huge difference between this classical occupation field and this noise quantum field. As we said yesterday, this classical field is, so to say, the symmetric combination of on the plus and minus contour. And we said yesterday, this field can take a finite expectation value. In particular, when we have a condensation going on, that would be described by this classical field here, scaling with the square root of the number of constituents in the system. So the phenomenon of the Bose condensation phenomenon comes with a macroscopic occupation of this classical mode here, phi classical. And if I move to real space, then this scales like n to the 0 because the particle total number of degrees of freedom and volume and extensive system, they scale alike. In contrast, as we discussed already yesterday, this quantum field can never undergo any kind of condensation phenomenon. So this field will always scale with n to the 0, nothing macroscopic going with this. And if I go to real space, then it actually strongly suppressed n to the minus 100. So this gives me now a great organizing principle for this action here that looks, for my taste, still too complicated. Namely, using this different counting of the classical and the quantum field, I can allow myself to only take into account second order in this quantum field terms. that's a great simplification. You can see here I've barred out the terms that are higher order. So this is third order in the quantum field, and that's another second order. Yeah, and we keep only linear terms in the quantum field and this noise term down here. Okay, so what this buys me, I can then reorganize this complete action here in terms of a form which has only linear terms in this quantum field and this single quadratic term. Okay, that's really a big simplification of this problem. In particular, this linear term, I can write it as the derivative of some auxiliary action, which has really the structure of an ordinary phi to the 4 theory. Yeah? So here you can see, oh, that's really like a Landau-Ginzburg functional that you learned, I guess, in some StatMech course. So the only point is I have a real Landau-Ginzburg functional and an imaginary Landau-Ginzburg functional. This part here is encoding all the dissipative terms that are acting on this system. And this term here is encoding all the reversible terms that are going on. But structurally, yeah, so they share really the same form. So now we can really analyze something like a phi-4 theory. And we have now also the equation of motion for this problem. I can formulate it like that. Yeah? And you can see immediately, this equation of motion has this nice invariance under this symmetry transformation here, under this classical symmetry transformation. Yeah? And to make life a little simple, yeah, we can ignore here this noise term, and we would also, in a simple mean field analysis, we would look at homogeneous fields, so we don't have any curvature effects in this problem. And then we would say, okay, we can analyze essentially the dynamics, this damping dynamics. Yeah, for the moment we bar out this term as well, and then I get the picture really of the motion. So if I initialize my system here, the field, yeah, then in this dissipative, if it's only undergoing this dissipative motion, it will just find this, the ball will roll downhill and find a point in this bottom of this sombrero potential. Yeah? And now you can see by symmetry, it can lie on all points in this rotationally invariant manifold, and it will just spontaneously choose one of these points here. Yeah? For example, the one that I've plotted here. And that's really the circumstance that happens when I have more pumping than I have losses. Then I have this down curvature here, and the system will find one of these minima here. Yeah? Now we've discarded this coherent term here. That's a bit of a detail. Yeah, one can see that really what determines, and it's intuitive, what it determines the stationary state is really the external dissipative forces that are acting on the system, the pumping and the losses, and this reversible dynamics that will just adjust itself and so to comply with this.
Sebastian, can I ask you a question? So I think in principle there is a phase transition between these two. I mean, when you have, there is a phase transition where you, I mean, at the equator, when you have equal no losses and drive, is where the transition is. Yes, do you see that there?
You can see that, yes, this parameter. Yeah, so this RD is a parameter that enters this dissipative Hamiltonian contribution here, and it can be positive or negative. If it is positive, then this HD looks roughly like that. Okay. So that's this gamma loss minus gamma pump bigger 0. So you have more losses than you have pumpings. Then intuitively the system ends up at 0 field, no condensation, no expectation value. Conversely, if gamma loss minus gamma pumping is smaller than 0, yeah, so then I have a negative curvature around the origin, and the system will somehow roll down to the sombrero potential, yeah, where the U1 symmetry here gives us this manifold of degenerate manifold.
Okay. Thanks. Perfect.
Okay, just to clarify,
Yeah.
so we assume that there is a condensation, and then it turns out that there actually is a condensation. Is that right? Like logic?
That's a very good remark. Yeah. So
okay.
I mean, to do this power counting analysis, yeah, this simplification of dropping the field, I've made this assumption, yeah, and somehow, but it justifies itself self-consistently. So when these conditions are realized, then you can do these simplifications. Then the logic is, let's then look at what happens physically. You see this circumstance, and then you, oh yeah, that's realized. So with hindsight, I was correct to do it like that. Yeah.
I see. Yeah, this is really cool. Thank you.
So it's a very important argument, yeah, to simplify this problem here.
I see. Thank you.
Okay, so now you can visually, it's really clear, yeah, so that we have this sombrero potential with this degenerate manifold of minima, and spontaneously the system will choose one of them. And also you see there's really no action cost. Yeah? When I want to move this order parameter, when I want to transform its phase, I will not modify the landscape here. So I will stay in this degenerate manifold. So this costs no action. An excitation, yeah, an angular excitation that moves me along this ground state manifold doesn't cost any action. And that is really nothing but rediscovering the Goldstone theorem in this Keldysh language. Yeah? So we can indeed say more generally, so the point was mainly to fiddle around, or to organize these degrees of freedom in the right way, these quantum fields and these classical fields. But now we really see that how this Goldstone theorem plays out, and spontaneous symmetry breaking can happen under equilibrium or non-equilibrium conditions. That doesn't matter at all. Yeah, all that matters is the presence of this U1 classical invariance and its spontaneous breaking by the spontaneous choice of one of these minima here in the bottom of the bottle of wine or in the sombrero potential. Yeah, and in particular, this is really a statement. Now we've developed this kind of in a case study, but it's really much more generally valid, and you can really demonstrate by essentially the same arguments as in equilibrium that there is this non-equilibrium Goldstone theorem as well. Okay, let me now, I think, final thing for this lecture, come to these conservation laws and what they have to do with these strong or quantum symmetries. And to this end, we go back now to this model M2, which really has, it's clear from scratch, yeah, but we want to develop the consequences, yeah, and then benefit from them. It's clear from scratch. These operators here are doing nothing but redistributing the superposition of particles in such a system here. So they commute with the total particle number. They conserve the total particle number. There's no number exchange with the bath. There can be entropy exchange, but no number exchange. If we do this on the Keldysh contour, yeah, then we have this, these operators here. When acting from left or right, they go to the plus or minus contour. And then indeed, you can see that this operator here has independent symmetry transformation. You can rotate the phase in this guy here when acting on the left of the density matrix and acting on the right of the density matrix. So indeed, we have here a larger symmetry. Yeah, we can do independent phase rotations on both these contours. And that's the circumstance where we said, okay, now we have a strong symmetry in the problem. Okay, good. And now it is really not more than looking up in your book on the Noether theorem, yeah, to construct these hydrodynamic modes. Yeah? And to walk you through it, what one does when one does a Noether construction, now we do it with this extra contour indices, we promote a global symmetry transformation, theta, classical and quantum. We promote it to local ones, and we study how does the action change under these local symmetry transformations. Yeah? So slowly varying local transformations. And then you get such a result, such a structure here, because we know that we have a symmetry. So whenever this configuration is really completely homogeneous, completely T and X dependent, then this term must vanish. And it does, because there's derivative operators acting on it. Yeah? So that's ensured by symmetry. So the leading term here is coming with these derivatives. Yeah? And there is one guy which connects the classical symmetry transformator C with some quantum object here, and the quantum generator with some other object, J classical. Yeah? We insist then in this Noether construction on the vanishing of the variation, and that immediately by partial integration gives us continuity equations. Yeah? So that's a continuity equation, and in particular note that we have actually two continuity equations for this, what we call classical and quantum currents. Yeah? Now, the form of these currents is maybe not that important, but I give you here two examples. Yeah? So the zero component, so this mu runs from 0, 1 to the number of dimensions that this system had. So this is temporal, and these are spatial. And the zero component of it is just this object here. Yeah? So the classical component is this one here, and the quantum is this one here. Okay, and then based on the continuity equation, when you have a continuity equation, maybe better in this form, we can immediately, according to this Noether construction, we can compute the charges, the Noether charges, by taking the spatial integral over the zero component of this Noether charge. Yeah? So that's really this manipulation. I take this equation here and I integrate it over X. We did that already on both sides. And because here is a gradient of something, this integration over a gradient of J will give me 0. Yeah? So then, and it's telling me that the time derivative of the spatial integral of the zero component equals 0. So therefore, I get a conserved charge by the object that stands here. And if you then look at how this plays out, yeah, you can see here the zero component of the quantum current here. That is now an object of this type, plus plus, expectation plus plus, minus expectation minus minus. Yeah? So that's again something that has to cancel, because we are so to say canceling the redundant information from the plus and minus contours. But if I add them up instead, and I look at this classical current, then I get really the total particle number. Yeah? So this is how this Keldysh formulation here tells you that the U1, and that's now the upshot of this, the U1 quantum symmetry is associated to a physical conserved charge, while the U1 classical symmetry is not associated to any interesting information. So that's the point of this construction here. We learn now that these strong symmetries, these quantum symmetries, they are the ones that are associated to conserved charges. Yeah. Okay. And I think for this, I would stop, and then I have to now really heavily think about how to still organize a bit the further material. I guess I just put a short summary of this. And, yeah.
Sounds great.
Other further questions?
For the classical part, do you think that phases can be something that is constant? Or, I mean, you said that in the classical there is no trivial particle number, but it can be encoded in coherences instead?
You mean whether there could be conservation laws in the case
in the coherences?
Classical symmetry?
Yes, when, I mean, you said, I mean, in these two strong symmetry, you're saying classically you don't get any trivial, I mean, NQ is equal to 0, but can you get something that is non-trivial in the coherences instead?
No. I mean, I would say so. I mean, this construction is quite rigid. Yeah. So it tells you. So then you would have to give me. So for this symmetry, for U1 phase rotation symmetry, the answer is clearly no, because this is kind of what we did there is exhaustive, really. So, I mean, you can only, so you have one kind of symmetry generators, you get one kind of current, and that's it. So no hope. If you give me a system with other symmetries, for example, there could be a strong parity symmetry, even in the absence of particle number conservation. Parity is a little weaker than really exact particle number conservation, so it's particle modulo 2. So that then you have then you could have some of that. Maybe Alexei will talk about that. I don't know. So then you could have other conservation laws associated to these symmetries as well. Okay. But for this kind of symmetry, that's the statement, and that's really rigid. Okay, again, the bottom line is really classical symmetries have to do with gapless modes in the sense of spontaneous symmetry breaking. Strong symmetries, quantum symmetries, are associated to conservation laws, and they also give you gapless modes in the sense of having a continuity equation. So that's also something that that describes slow dynamical modes in your problem.
Great.
Can I ask you a question here? What's the role of the crystal symmetries here? So if I start with a system that has CN symmetry, rotational symmetries, does that affect any way all of these calculations? I
mean, so for any symmetry that you can play this game here. So I would say whatever it's more a framing. So so the construction would always be the same. For a translational symmetry or rotational symmetry, you would take your field, and now we have it plus minus, and you can have, for example, t and x plus a. So that would be translational symmetry, or you could have a rotation on this vector x. But you also you see that I can add this. I can decorate this generator of the symmetry again with a plus and minus index. I could, and then the question is again, does this happen? Do I have a strong symmetry, a strong translational symmetry, or only a weak translational symmetry? So that's really the fun point of it. So that I mean, the concept is absolutely general. And here is really how it generalizes. So, and the statement is when you have this double, so when you have kind of the translation symmetry on the plus times translation on the minus contour, then you would have a conserved total momentum. So otherwise, and if you only have a weak symmetry, then you don't. But, I mean, one thing that maybe I should stress, is that for a Hamiltonian piece, they always come together. That's also an important, interesting insight. So if I have some dissipator still acting on, but it's very clear by this structure of this von Neumann or Schrödinger equation here. It's crystal clear that for a Hamiltonian, the strong and the weak symmetries always coincide, because they do not couple. The problem is always in this guy. In this guy, this can couple to the outer world, physically speaking. And therefore, this, for example, for the particle number exchange, this is extremely transparent. This fluctuation, this jump term is the one that will kick out particles of the system that I'm describing with this density operator rho, or push it back into the system. That's the point. While for a Hamiltonian, it's always really these two symmetries always coincide, because there is no talking to the outer world that is really encoded in this fluctuation term here. And the problem is absolutely not in these guys, in this anti-commutator term that we discussed. And so this, again, is of the structure that doesn't is of a structure as a Hamiltonian. Yeah? This guy here is making the difference.
And I have also another question. For all of this system, you assume some sort of the gap, so half filling. But if the system was semi-metal, was a metal, then there was no obvious gap in the system. How this picture works?
Yeah, very, very good point. I mean, you should even ask more broadly, what is actually the gap in an open system? Yeah. Right. Yeah, I mean, it's not obvious in a Hamiltonian, and I mean, maybe we do. I do part of the.
Or Sebastian, one question: if you are going to go back to this, maybe we can break. Maybe this could be.
We can break it.
We
can discuss it via Discord. I'm really happy to. I mean, I have time the whole evening.
But you are going to cover anyway that, so maybe, because I wouldn't want people to get exhausted because it will continue until 12:30. So one possibility is to break here, take 20 minutes break. We go back, I mean, 11:05. So we, and then if it's necessary, we cover that. Sebastian is going to go cover partially that, and then we can continue as necessary. But let's respect the break and let him stretch a little bit, because 3 hours of lecture is very much. So thank you.
Yeah. Okay. Thank you. So when do we meet again?
Let's meet at 11:05. So you have 20.
Okay.
Perfect.
And question is noted. We can discuss it later.
Thank you.